now this is a completely different topic. As I mentioned, this is now, I really need to get used to this pointer. This is about the safety assessment of steels under ultra-low cycle fatigue loading conditions, and here we are going to use a phenomenological damage mechanics model. The whole study was motivated by civil engineering. So there is, on the one hand, in many regions in the world, what you can see in here, high risk of seismic events. There has also been severe damage to many infrastructure applications, more or less all over the world. But unfortunately, if you look over the different design rules and take the European code as an example, there is usually only an empirical safety assessment available, usually that even does not consider the toughness of the materials. So there is a guideline for the selection of the steel grade, but this is usually only based on the strength properties of the materials, but not explicitly also relies on the toughness properties of the material. In order to improve the safety assessment, we would like to define a toughness-based criterion for the selection of steel grades. For this, we also need to make use of a damage mechanics model that is able to predict ultra-low cycle fatigue damage. Okay, the model itself shall be able to consider the effect of cyclic plasticity in order to have a good description of the stress-strain response under large strain amplitudes, or the cyclic loads with large strain amplitudes, because we want to make use of a strain-based model, so we need to be sure that our calculated strains are really correct. For the effective strain concept, we need to consider the effect of reversal loading on damage, because not every equivalent plastic strain will really contribute to ductile damage. So we need to make sure, or we need to invent a effective strain concept. And of course, we also want to take into consideration that damage will induce some softening of the component. For the cyclic plasticity model, we have made use of an existing kinematic hardening law. It's the so-called, I hope I pronounced it correctly, Yoshida-Uemori model, which makes use of two yield surfaces. Both, in our case, are only described by kinematic hardening. Usually there's also the possibility to have isotropic hardening for the bounding surface, but we did not make use of this. Okay, the effective strain concept shall take into consideration that, in contrast to the monotonic loading, where all the dislocation slip will also contribute to nucleation of voids and formation of ductile damage. In reversal loading, we can also have some kind of healing effect, because there's also a chance that the dislocations are slipping in the opposite direction. And of course, this has to be considered by the model.
It's important to the
Okay, then I'll use this. So we have defined an effective strain measure. Very simple one, by the way. There are, to my knowledge, even more sophisticated ones in literature. Here we only said that our equivalent plastic strain only counts as relevant for ductile damage evolution when the stress reactivity is positive, so when the material is under a tension load. And all the increase in equivalent plastic strain will then also serve as increase in effective strain. So in fact, if you've got a plot where you have the effective strain over the equivalent plastic strain, you see that this results in a stepwise function. Okay, and there's also a ductile damage evolution law. There's no threshold values, no damage initiation criterion, so we assume that ductile damage will initiate from the onset of plastic yielding, and it can increase until a critical damage arrival is reached, and there's a certain function to describe damage evolution in between. Of course, we need to couple the damage evolution back into our yield potential in order to describe the influence of damage on the on the constitutive behavior. we would only apply a plasticity model, we would always run into the hardening phase, but here there can also be a damage-induced softening, and this shall be expressed as well by the model. Okay, so for the cyclic plasticity, we have selected the Yoshida-Uemori model. There's the effective strain concept that I presented, and the ductile damage evolution law, and all this contains some parameters that need to be calibrated. All this has been done with the help of cyclic experiment with unnotched and notched specimens. We applied 2 loading amplitudes, plus minus 0.2 and plus minus 0.4 millimeters at a rather slow loading rate. Here you see the simulation models that we used. So the element size is quite small, it's 0.15 millimeters. The model itself was implemented as a VU-MAT for Abacus. And here you see some results of our material parameter calibration. There is already quite a good agreement between the experimental and numerical results in this case, but you should please consider that so far the damage evolution parameters were not calibrated, so there is in other words no need to have the perfect match in here, because damage evolution is not considered. This is then to be done in the next step, and here we also made a very simple approach to characterize the damage evolution during our test, because we simply plotted the ratio of stress applied in a certain cycle compared to the initial value over the number of cycles. So we could see how much in this strain controlled or displacement controlled experiment, how much the strength of the material decreased, and of course this is a result of damage, and here we could calibrate the parameters of our damage evolution law. Here you can then see the full set of parameters that were used for this model. You see that also here for the plus minus 0.2 experiment, the agreement is much better than we saw earlier when only the plasticity parameters were calibrated. And here you also see after the calibration the values of the damage evolution law. We also validated this with the notch specimens, and also here the agreement between experiment and simulation is quite well. And also here you see that for both cases, for both loading amplitudes, we were able to match the number of cycles until break, or breakage of the sample agrees very well between experiment and simulation. Now the question is, how can we determine the toughness requirement? The idea is that first of all we show that our model is able to predict the behavior of a full component. Then we identify, that doesn't properly work anymore, we identify a set of damage parameters, a virtual set of parameters that will result in simulations in the desired performance of the component. So it doesn't mean we speak about the existing material anymore, but we really think about a material that would withstand the applied loads in a desired way. So we invent a virtual set of damage parameters, and then we also use this virtual set of parameters to simulate Charpy test. That is possible. I do not have the time, I guess, to speak about this in my presentation, but we've shown that this is possible. And like this, you can identify upper shelf requirements, toughness requirements for your material. So to conclude, I've spoken about the development of a damage mechanics model for ultra-low cycle fatigue. The core parts of this model are the cycle plasticity model, the effective strain concept, and the damage evolution law. The next step would be, if you want to derive the toughness requirements, would be to simulate the large-scale test with the damage mechanics model in order to determine the desired virtual set of damage parameters that guarantees the desired component behavior. Of course, you have to show that your model is really applicable to these large-scale structures. We have proven this with pipeline elbows under inner pressure of 20 bars
that were also subjected to ultra-low cycle fatigue bending operations. And finally, as I mentioned, you can then derive the required toughness properties by simulation of jumpy tests. But it has to be noted here that I did not speak about any cleavage fracture criterion that also should be coupled into the model to make sure that you don't have transition behavior, or at least that you are able to predict the case that you have transition behavior. And with this, I would also like to close my second contribution. Thank you very much.